Welcome everyone to our November first Fridays on bass bars. And this will actually be part one of a two-part presentation because there's so much results to present that there will be a part two for December. So we will actually move Professor Woodhouse's presentation on wood to January. You'll get update emails to re-register for all of that. Joseph?
Hello, everyone. So the bass bar, there's actually very little in the research literature about, surprisingly enough, compared with, let's say, the bridge or archings or graduations. And we've talked about doing a bass bar experiment at Oberlin for a long time, but it's very difficult one to mount. You need a lot of makers and enough instruments to get a reasonable sample. But we managed to pull it off last summer, and although we learned a lot in the process about how to run experiments, I think it went very well, and I'm very grateful for especially the makers who basically brought instruments with pre-installed bass bars and then opened them and closed them every day after adjustments, and everyone stuck to schedule. Although we had a bass bar height experiment and a scoop experiment, and from each of those we lost one set of data because of things beyond our control that happened to the instruments or the data, but still we have 4 violins in one group and 5 in another, so we think it's enough to suggest some interesting results. 2 kinds of measurements, admittance and radiation. Lonnie on the laser rig and MJ on the radiation rig. And thanks to both of them, they worked very long hours and herded violin makers in and out, and stayed up all night analyzing things. Colin did internal microphone measurements of every instrument there, and George did a modal analysis on, I think, several, and we'll hear from them next month. Big thanks to Chris Rogers, who in real time was making amendments to the software that we were using, and to the analysis pages later. And then in the background, keeping us tethered to reality, were Evan and Jim as usual. And without them, we probably would have gone wildly wrong. So let me just very briefly review some of the measurements. Measuring sound radiation, we tapped the bridge on the side and or on the top with this impulse hammer, which measures the force of the blow. A microphone picks up the signal. We measure around the instrument in 12 positions, and we get a typical radiation spectrum here. We have at low frequencies, the so-called signature modes, and then the transition hill, the bridge hill, the upper hill. These are characterized by a lot of overlapping modes, where these lower ones are individual modes where you can track their frequencies individually. One way of looking at things that is to put band levels, where you can see an average level for different frequency bands, and all sorts of bands have been proposed. I'll introduce the ones I'm going to use later on. Well, actually, let me just say right now, these are not based on any kind of psychoacoustical properties. They're simply that if you look at a lot of any group of violins, really, the spectrum tends to have lows in these points, so it's convenient to divide it up that way. Repeatability, I did a test a year ago, taking a instrument in and out of the rig, doing one set, just a set of 10 hammer taps at one position, and it was quite good. And so, but keep these in mind. So plus or minus half a dB, let's say, keep them in mind when we're looking at measurements. And Claudia Fritz found that just notable differences for band averages have to be at least 1 to 3 dB in level. So we're hopefully within the in the range of meaningful differences here. The most likely source of error is almost certainly the repeated removal and replacement of the tops. If we'd had one more maker, or it would have been good, I suppose, to have them simply take off and remove the top and measure it each time. And maybe we could still do that experiment at some time, but right now we don't know how big that variable is. Though in my experience, working on my own instruments, I don't find that replacing the top makes a big difference. So if we're going to judge spectrum, we need to say what makes it better, what makes it worse. And of course, there's been all sorts of ideas of what's called objective quality parameters, and popular ones show this sort of a shape where you want a lot of energy in the signature modes, not too much in the transition hill, plenty in the bridge hill, and not too much in the upper. But these depth and fullness, totality, brilliance, harshness, really there's no subjective testing to back these up. Not to say they're wrong necessarily, but in my experience, there's good violins that have that and that don't have that. Another set of research shows that evenness across the spectrum, in other words, having as equal in these levels is helpful, or at least having no big gaps. And once again, there's not really any subjective testing. So how do we decide whether one bass bar is better than the other? For me, I just like to get a lot of sound in all areas. I can't say that I'm worried about having too much, maybe in this band if it's low elsewhere, but it's pretty rare that one sees that. So, and as a maker too, I think the main thing, we have to deal with a variety of clients. So what would be great would be know how to adjust the levels in each band independently, or at very least see how we can see how the bass bar affects these relative band levels. So the first test was bass bar height, and MJ created these lovely drawings, and we started with something that was probably higher than we'd ever used, 14 millimeters, and went down to 7.3. And we did it, the reason the numbers aren't round numbers is we did it by a fixed percentage. So at each point in the bar, or at the measuring points, we took the heights down by the same percentage each time. And that seemed to us more meaningful than keeping to some arbitrary numbers because of shop practice. This is an average. Oh, let me just hide my. Okay, so this is an average spectrum of this is an average spectrum of the horizontal and vertical radiation measurements for all of the instruments as they came into the workshop. Now, so that would be measurement number 1. This would be measurement number 1 compared with number 2 in red, where we take the height down to just below 12, and we can see we're getting something close to a normal bar, and we see an increase in all the frequency bands. Now, the red is still measurement 2. When we get to measurement 3, going down to about 10 millimeters, we're suddenly losing in the upper 3. Not much change, a little onto 4. And then going to the very lowest, we see a distinct drop in the highest and all over. Funny enough, a little bit better here in the Bridge Hill region. So if one is going for the most sound in all the bands, then height number 2 is the clear winner there. I will say now, and I'll say it later, this is an average of all 4 instruments. The next step, one of the next steps I'm going to take, and perhaps can show some results in the next meeting, is how it varies with individual instruments. And are there some individual instruments where, that are dragging the average one way or the other? Okay, now this was using horizontal radiation, where we're tapping the side of the bridge, as well as vertical, where we tap the top of the bridge, and we get much more excited in the top band with that. Do we get the same results using horizontal radiation? And the answer is yes. Red here is the step 2, and we see it's a clear winner. Now, if we use admittance, let's say instead of let's say you are only measuring admittance and not radiation, would you get the same results? Well, kind of. It's much less clear. This is 2 and 4. So the red is against all the others. So the red actually does rather worse in the bass, and it's good in the bridge hill, and yeah, it's pretty good elsewhere, but it's not quite as clear a result. We could also say that reducing the height increases the relative output at low frequencies, which I guess is, I think, what all of us would expect. If your instrument's a little bright, you'd think about lowering the bar. If it needs more brilliance, you'd think about raising the bar. So this is just 2 bands, and it shows the shift between 1 and 5. Here is the scoop experiment, where we, as you can see, we changed the profile, keeping the end heights and the center heights the same for each iteration. And we start at the same height as it happens, the preferred result from step 2 from the height experiment. And so we're going from 1 to C, 1 to 2. So the top is probably flatter than most of us do it. This is a more normal scoop, and indeed we see a boost in the top 3 bands. Not much change to 3. And this surprised me. We're going to step 4, and suddenly we get an increase everywhere. So it seems that stage 4 provides higher output in all frequency bands, which surprises me. So which is great, because I've often wondered. I sort of grew up thinking that we wanted more height toward the edges as sort of a reaction to the very scooped bars you see sometimes, and that sort of have a look of inefficiency to me. But this was interesting. It'll be particularly interesting to look at the individual instruments and say which ones this was most true for. Now, the last step, we took the end of the bar down to 0, so everything else stayed the same. And this kind of answers a question: do we need height at the end of the bar? Somebody's breaking in here. And what we see that was with the end of the bar down to 0, all band levels down, except for the bridge hill. We get these 2 interesting peaks. Now, I find that fascinating. I don't know what to make of it. I wouldn't take the ends of the bar off just to get that boost particularly, because you do lose in the other areas. But it would be interesting to know, maybe from Cullen's work, what the physical reasons for that are. Or this, of course, could just be the luck of the draw with these particular instruments. So Johann Lotter was kind enough to do an extra step, or he took the initiative to do that, and he removed the bar altogether. And this, again, I find interesting. I always thought that the bass bar was in some way responsible for making one side of the instrument move together, and therefore getting more bass, tying the diaphragm together. But no, it gives much more bass by removing the bar altogether. So we really can't talk of it as a bass bar, except that it's on the bass side. It's really affecting the balance between bass and treble profoundly. And of course, it's holding up the instrument, against the string edge. There's a lot of other reasons for it. But this I find interesting. And also, the frequency did not drop very much when in our first 5 steps in the height. This is the height experiment. No, excuse me. This was from the height experiment. The frequencies dropped much less than I would have thought. But when you get the bar off altogether, especially B1 plus drops in frequency. That's probably could be explained by those who do modal analysis. Okay, so measuring bridge admittance. Admittance is the velocity at the driving point per unit driving force. So it measures the energy going into the violin from the strings, where radiation measures what comes out. So this, I've taken a single violin and I've normalized the levels. In other words, made both have the same average level. The red being radiation and the the red being admittance and the black being radiation. And you can see right away there's some big differences. The most profound one, well, famously, is at A0, where there's very little movement for a lot of output. Then there's recognizable peaks in both. They start to diverge in an interesting way, I think, around the bridge hill. The bridge hill concept originated with measurements of admittance. So it's interesting to find, and I find this utterly consistent across probably 150 instruments I've measured. The radiation peaks are always lower. For some reason or another, you don't see, you see less radiation here. And then they kind of track each other at higher frequencies. So if we define efficiency as low admittance together with high radiation, in other words, let's say it's efficient if you have to move the bridge very little to get a lot of sound. And we look at these graphs in that sense, and we see that A0 here is very efficient. These are pretty good. This is extremely efficient, but whenever you're measuring something in a valley, you have to worry about noise. So I don't know how reliable that is, but it's pretty good here. And then there's this inefficient area here. And I would be very interested in learning why that's the case. And then they pretty much track each other at higher frequencies. So what does this have to do with the bass bar? How does bass bar height affect efficiency in this very general sense? Admittance is up here, radiation is down here. Stage 1 black, stage 5 red. We can see that admittance, it goes up slightly. In other words, the amount of motion in the bridge goes up and the amount of radiation goes down. So that, again, in a general sense, a low bass bar seems to make the instrument less efficient. What does that mean for a player? We don't really know. If it were a straight line like this, if we're talking about efficiency globally went up and down, that would be easy to imagine. A violin where it took very little string force, very little effort, you'd get a lot of sound. That's quite easy to imagine. It's more difficult to imagine when you start looking at it by the region. And here it is with the lower band 200 to 780, and then a big band 780 to 7,000. We see that it's slightly less efficient going from stage 1 to 5, but it's clearly less efficient in the lower frequencies. So it seems again that a lower bass bar reduces efficiency predominantly at low frequencies. And I don't know what that means. That would take a lot of thinking and psychoacoustic testing. If lower frequencies are less efficient, how does that feel to the player? It could certainly mean more wolf notes because you've got higher admittance. But other than that, I don't have a good intuition. Now, if we break it up even more by our 4 frequency bands, we see a bit less, perhaps wolfier, a bit less, a bit more, and slightly more, going from stage 1 to stage 5. And again, these are the average horizontal admittance and horizontal radiation for all violins on the bass bar height. So the conclusions, to the extent that we can extrapolate from these small number of instruments, we have the best height seems to be 12 millimeters or just under, and just under 4 at the end, 3.8, nothing very shocking. More surprising to me is this seems to be the best profile, the same heights at the end, but more scooped here. I'm curious to look next at how this varies for individual instruments. Can we relate this to the particular archings, especially the longitudinal profiles, to the model? This is the sort of question I think that would be ideally answered if someone would create a FEA model, the sort of thing that Colin has done, and I think Sean Hardesty is working on. But if we could have a good model and then start tweaking these areas which experimental results point to, but don't give us hard results on, that would be great. So reducing bassbar height tends to increase radiation at low frequencies while dropping it at high. That goes with common practice. And also admittance measurements are not good predictors of radiation, and the above conclusions are based on radiation. For the sort of work I'm doing, measuring radiation makes sense if you're relating bassbar adjustments to elements of playability, the sort of thing that Jim Woodhouse has studied extensively, then clearly one could reanalyze the data with that in mind. I hope to have some more to add next month, or failing that, I want to write this whole thing up as a paper. But I will turn it over to MJ now. We actually, unusually, we haven't coordinated. We finally got a clean data set after a lot of time and sorting, and so MJ's did her thing, I did mine, so there'll be some overlap, but I hope that's all for the best, seeing things from a couple of points of view. And MJ will be making a presentation at the VSA in I guess a week. So over to you, MJ.
Joseph, so that's a typo, right? While decreasing at high.
Whoops, sorry.
No, but back to your conclusion. Is that a typo? Reducing bassbar height increases radiation at low frequency while
increasing it at yeah, you're absolutely right. I'm sorry.
No, you spoke correctly, but it's a typo in this slide. Okay.
Apologies.
Point that out.
I will change it. Thanks. I will stop sharing. So we'll hold your questions till after MJ's done. MJ, would you like to share?
Yeah. Hello, everyone. How do I do this? Oops. All the way down here. Okay. All right. Let me figure out how to full screen this. Sorry, moment. Is it okay?
Okay.
Okay.
We got it.
Okay. Yeah, so some overlap in what we are talking about, but basically, I'm gonna run over a little bit. So I broke it down into both experiments, and so in the height experiment, I just want to show a little overview of. Okay, yeah. So here's our iterations chart and the detailed measurements that that we showed earlier, but this one is a little more detailed. It's in eighths.
So did it go down a fixed percentage? What was the percentage it went down every time? I meant to ask you that.
It was 15% from, yeah, so starting at 14 in the middle, okay, and 4.5 at the ends, and this is not including the plate. So, you know, if you had, yeah, basically if you had like a 2.5 millimeter plate or 3 millimeter plate, then that would be 17 through the plate, if that's how you measure. And then, yeah, so then by the end, after doing a 15% reduction at every stage, then the fifth iteration is like 7.3 millimeter bar in the middle and 2.3 millimeters at the ends. Next, okay, so here are the 4 instruments, and we collected a little bit of information about each. In retrospect, it would have been great to collect a lot more, but sometimes, yeah, it's hard to get everything together. So actually I'm missing some arch heights on some of the instruments as well, but just as an overview, like the instruments, like the highest arched one was 16.8 millimeters, and the lowest arched one was 15.4. I think the Curtin one is something like 15.5. I just got that from Alex. So anyway, yeah. and then the graduations varied from like a pretty thick one here, you know, like 3.3, 3 point, you know, this is the graduations right under the bar. And then down to like a plate that was like 2.2 all over, or like here and there, and 2.5 basically. The range of masses of these plates were yeah, so there was a pretty light one. That's actually the one that was in the last slide, the thinnest graduations. And then the heaviest plate is not the one that was the thickest graduations, but yeah, so this shows the range of like the masses. This first point here is the plate with no bar. So it ranged from 55 to 76 grams. And then, yeah, then you just get an even decline as you take the bar down. Okay, the free plate modes ranged from, yeah, so the starting points for mode 5 range from 313 to 330. And actually I should have used the green one here. But yeah, so the heaviest, I mean, the highest mode 2 was starting around 160. And then the lowest mode 2 was starting around 138 without bar. And then we calculated the Z Evans number, Evan Davis's, I guess like impedance, mechanical impedance number or something, where you're taking the mass and the frequencies and trying to figure out like a sort of stand-in number for stiffness for the strength of the plate. And so yeah, so combining them, then basically yeah, this is sort of the range of so we have sort of four different strengths of plate to look at in this. And what I was interested in seeing is, I think the main question that I went into with this experiment was, how would, you know, putting these specifically sized bars in interact with like different types of plates, basically different strengths of plates. So yeah, now we can go on. So yeah, keep an eye on Barnes and Lauder. So the strongest plate was Barnes here, the blue one, and then the most flexible plate was Lauder's. Okay, and Joe already introduced the radiation measurements and what they are, and I just put 2 links if people want to check out more. The bottom one is a link to Chris Rogers' software, which is what we use to collect all of the data here. Okay, so yeah, so this is the average of 5 instruments, even though actually the data set should just be 4, but yeah. This one has an extra one in it, so I have to redo this later. But anyway, so this is the first iteration, and then the second iteration, and the third iteration, and this is the average of all 5 instruments per iteration. We're going to look at it more clearly broken down, but I just wanted to run through these. And then yeah, okay, so here's the average of the 5 instruments all at each iteration, shown all together and then smoothed, so that you can kind of not look at so many squiggles all at once. It's in rainbow order, so the first iteration is red, and then yellow, green, blue, purple. So the 5th iteration is purple, and the first iteration is red. And then you can see sort of higher output on the on average with the yellow curve, which is the second iteration. So I show it again in this way. So basically, you know, okay, yeah, let me go back here. So we have these band averages that Joe had already described. We have like the signature mode region from 200 to 780-ish, and then the transition hill, and then the bridge hill and the treble slope. And so what I'm doing in the next slide is taking basically taking these and turning them into a bar chart so you can see the movement per iteration. So in the signature modes, the first iteration, this is the band average for that average amplitude there. And then the second iteration is shown here, third, fourth, fifth. And then for the transition hill, same thing. So you can see the movement of each zone a little bit more clearly, since they're all smashed onto top of each other in the last slide. Yeah, so for me, what just jumps out is that like yellow wins all the time, and so that's the normal thing that we do. So that's good. So for the strongest plate, this is how the strongest plate responded. Yeah, so okay, so now I'm just breaking it into, I want to look at how it looks for one instrument. So this is Dorian's instrument, and okay, so I'm gonna look at Dorian's versus, so the strongest plate versus the most flexible plate. This is what it looks like. I'm not gonna go into like mode detail here, but I'm gonna look at the band averages again in the next couple slides. So for Dorian, for Barnes, this is how it looked, and actually, yeah. So for the strongest plate, with the lowering of the bar, you actually get more output for this instrument in the signature modes. And then there's some, I don't know, everything's within, half a dB or something. So I don't really know, like some of this could be measurement error. Since this is just, we're looking at one instrument, although it is band averages. So yeah, and then for the most flexible plate, which is Lauder's, this one I feel like is more clearly showing that like there's a amplitude boost in the second iteration for transition hill, bridge hill, and treble slope, though curiously not really for the signature notes. Yeah, and then here's the with no bar. Yeah. You get a giant boost in the signature mode.
Hey, Ben.
You like lose all your treble here. Oh, okay. So my conclusion from the height experiment is keep doing what you're doing. So yeah, if this is sort of, yeah, basically ballpark what I think most of the people who participated, and myself included, consider sort of the normal bar heights that we learn. Yeah, stick with that. All right. So for the profile experiment, these were our participants, but yeah, one of the instruments was incomplete, so we dropped it from the analysis. And here are the heights, which we saw earlier. And yeah, basically, I don't actually quite remember how I generated this, but yeah, you can see that all of the reduction is sort of in this quarter, and then everything's blended over. And then at the last stage, we just chop off the ends as well. So again, running through the instruments that participated, this is a summary of them. I'm missing a lot of arch heights here, but yeah, so the graduations under the bar. We have a very thick instrument that was like 3/8 in the middle, basically. And then we have a very, on the thinner side instrument down here, 2.4, 2.5 millimeters thickness. Interestingly, for the instruments that we had for this experiment, they kind of grouped into, like, there's one really flexible one, and then there's like 4 that are on the heavier side. And then if you look at the modes, then they shake out this way. And yeah, so ranging from starting place for mode 5, it ranges from 308, actually lower than 308, to 340 hertz. And then for the mode 2 then 120 to 141. So then if you combine mass and frequency in Evans' formula, then you get the P3 McCann as the sort of stiffest plate or strongest plate, and then P4 Reitenberger as like the most flexible plate. And again, they're like quite grouped, or like these upper four kind of crossover and are in the same area, and then there's just one that's significantly more flexible than the rest. So we'll look at those and how they interact with the different profiles as well. Did I say Mattis? Oh, okay, well, anyway, so yeah, I think actually it was McCann's that's the heaviest or the stiffest. Okay, so same thing here. We're just gonna run through the average of, this was the average of 6 instruments, but there's an incomplete set, so I need to redo the slides again. I forgot. But yeah, so this is the first iteration, second iteration, third iteration, fourth, and the fifth. And then I find it easier to look at the detail together. And so I didn't label this one. This is the 5 iterations, the average of all the instruments shown in rainbow order. So basically, yeah, red is the first iteration, and then purple is the last one. And so again, I'm going to pull apart the band averages here. Hold on, my mouse is dying. Okay, so for the band averages, yeah, so yeah, everything is quite close to each other. So like, yeah, again, I don't see a very clear trend here immediately. I think, let's move on here. If you look at individual instruments, then you can see some like trending movement per instrument, but they're not consistent with each other. So this is Mattis's, which is the red line here. This is in the stiffness, this is that stiffness chart, basically the strength or the Z number chart. And so basically this is this red line is the instrument that we're looking at here. And then these are the iterations of the profiles. So in the signature modes, everything's dropping as you scoop the bar out, and the transition hill as well. Then it peaks out at the second iteration. And then I'm not going to say any pattern for these upper two. Yeah. For Beilhardt's, P1. P1 is also a middle of the road one, basically. So the strength is on the lower end of that upper grouping. And there's a trend for the transition hill and the bridge hill, like everything's overall going up. It looks like the third iteration, there's higher output for those. And I think the third iteration is kind of a normal scooping for a lot of makers as well. Yeah, and the comment for the third iteration was not as loud as the others, even though our thing shows higher output there. Very easy to play and can dig into the string and get the response I want. So, okay, and then for the really flexible instrument, this one has somewhat clear trend lines also in the signature modes region and the transition hill region. And yeah. So basically what I thought I had seen before was that there was a for the really flexible instrument, the more you scoop the bar out, the higher the output, basically the output goes up and up. And then for one of the stiffer instruments, it was the opposite. let me see where it is. Yeah, for Mattis's, which is one of the stiffer instruments, then as you then it benefits more from like a fuller bar. But if you look at everything all together, then basically, for me, what I think is that there are visible trends within individual instruments, but there's too many other unrecorded parameters to know exactly what's going with what. So like for me personally, I was looking at the stiffness of the plate as something to like see if there is a correlation with, but it could be with a million other variables that we don't have fleshed out. And so more study needed here. That's all I got for y'all.
Right. Thank you, MJ and Joseph. Yes, let's start with some questions that's in the chat. First question is, how were sound posts handled?
Yeah, before we do that, MJ, can you stop sharing your screen so that we can see the population? Thanks. How were what handled?
Sound posts.
I think people simply replaced them in the same position. Alex, did people mark the positions?
I believe they did. Yeah. That was discussed at the beginning of the experiment. I don't know how strict we were about that, but yeah.
So the general idea was try and get everything back as it was before, or to stay consistent.
And then another question was, what was the density of the bar material?
Alex, did we prepare the bar material? I can't remember anymore. Or did people bring their own?
We did collect some information about it, and so for actually, I have numbers for those, but I didn't display them, and I don't have numbers for everybody, but a lot of people in the height experiment used quite high density bars, so ranging from 0.41 to 0.45. The only one that was less than that was Alex's. And then the profile experiment, people had bars between 0.36 and 0.42. So that was not controlled for, basically.
So if we're doing this experiment again, or I guess maybe even putting studs around the bass bars, I mean the sound posts, so they all go back in the same place every time. Little studs might help. And then having one source of bass bar would, although, does a heavy instrument need a heavier bar? There's, it's hard to make sense of some controls. Next question.
And the next question in the chat is, what about the cross profile during the lowering process?
We didn't cover anything, that we kept straight walls and then just
yeah, so we did have, at the beginning of the experiment, we did have little templates that were kind of semicircle shapes, just to kind of give a general reference. But in general, it was straight sides with a semicircle on top, just for consistency's sake, rather than having complex parabolic shapes.
We figured that way people are more likely to do similar things than if they use their own personal cross sections. So we came up with something maybe a little unnatural, but more consistent.
And then were the high points at the center or stop or in between?
The center.
Right. Any questions from the audience? You can use, if you could use the raise hands function. Oh, Colin has manually raised his hands. I see that. Colin, go ahead.
I thought I got a hand up. The thing that comes out of this particularly, quite apart from the fact that the bass bar appears to have far less influence, in fact, on the overall output over the whole frequency range, compared to the 1 to 2 dB change that's just perceptible. I mean, we're right on the limits of what you might be able to hear in fact, in changing the sound of the instrument, which is a surprising thing. But the other thing that I think I'd like to compliment the makers, because I mean, the amazing thing is that having said that, when you put the instruments back together again, the results are always within half a dB or something like that, which I think is extraordinary too. So that taking the whole instrument apart 5 times, putting it back together again, the changes, in fact, are incredibly small. And
Well,
that shows you something about the skills of the maker, and when you're doing an experiment like this, and it shows you can take the top off and put it back again, and you're not going to make major changes in the overall output of the instrument.
That I agree with completely. Good shot practice means you have the same instruments again and again. I do think, though, that to say that the bass bar is a small effect is tricky, because it can make. Well, first of all, when you average things, you lose the differences in peaks, and sometimes, there can be quite large peak changes, which I think the ear can pick out easily, even though the average in a band doesn't shift much. But then we get into that very complicated question of what do people perceive, and out in the real world, players are incredibly fussy about apparently small changes, and in the research site, we're a hard time pinning down listeners with fairly large ones, so that we have to keep working on. Don, I think, had his hand up.
Yeah, one thing that concerns me is that when you lower the bass bar, you're also reducing the mass. So you can't really separate out what effect is due to stiffness and what's due to a mass difference. Now, I've done some things on that. One particular was at the VMAI competition. I put a 2-gram chunk of clay on top of the bass bar right in front of the bridge. And the audience that was listening preferred it with the 2-gram weight of clay on it. But me as the player, I didn't like it at all, because it was kind of muted a little bit. One other thing is that I did the remove bass bar experiment, and the results I got were very similar. The B1 plus resonance was unplayably wolfy. So it tells you that the admittance was ridiculously high at that point.
Oh, cool. Now, in terms of separating stiffness and mass, it wasn't really important for this experiment, because we were just talking about lowering bars overall. But I agree with that as 2 parameters, and one could experiment with that by using woods of different densities and tuning them. You'd have to be careful with the tap tones. There's some sort of an experiment there where you could separate. And I remember Charles Besnay knew, a French researcher. He had the notion that the most important function of the bar was mass rather than stiffness. And I don't particularly agree with that, but I would say that yes, it has to be a factor too. I've done things like putting small amounts of clay all along the bass bar, which kind of simulates denser wood, and you kind of get the effect you have of putting more mass. It's not especially sensitive there, but you'll tend to get a little less output in some of the frequency ranges, and some small drops in frequency of some modes. An interesting observations, Don. Luca?
Thank you. Both of you mentioned, especially I think in the height experiment, there seemed to be an optimum at the 11.9 millimeter height, which maybe the physicists can answer my question a little bit better. It seems not reasonable to me that there should be a non-linearity there. Shouldn't they just linearly move if you change the height? And there shouldn't be an optimum point, especially considering that the plates were very different. And if we can maybe think that there's an optimum bass bar for a given plate, but that wouldn't be the same for 5 very different plates. So I would maybe look at, I don't know, did we record humidity data or something? Like, this seems like an error to me. You can't really physically imagine that to happen at all. I don't know, maybe some of the physicists can chime in.
Hold on, could you just say that again? You would expect what to change linearly?
Just, for example, the frequency of the B1 mode, for example, would move in a linear fashion if you lower the bass bar, right? You wouldn't expect it to jump at some points.
The frequency, no, and indeed it doesn't.
It could
That's
never
right.
go up if I'm removing material, right?
Yes.
It could theoretically if it's just mass effect. In most cases, it will just go down.
Mhm.
And we were looking at the average levels in bands and frequency
Mhm.
bands, and there seemed to be an optimum at the second iteration, which was, I think, 11.9 millimeter height.
Mhm.
And in the same sense, I can't really imagine there to be a jump there. It doesn't seem feasible to me physically.
It
In the
doesn't seem.
simulation, for example, if I change the height of the bass bar, I can't get it like an optimum at that frequency, at that height. I usually just get a trend downwards, which might not be strictly linear. It could be going down faster at some points, but it can never go up and then down. It must be linear in one direction.
What can't? The output?
The output.
That's not my experience. I find all sorts of little things can boost. I mean, sometimes a sound post adjustment, sometimes a change in bass bar, sometimes humidity, as you say.
But lowering it and getting a higher level, then lowering it some more and then getting a lower level again. This rise, it doesn't seem feasible to me just physically. I would look at the measurements and see if there's an error there.
Absolutely. But I wonder, though, whether the fact that the admittance and the radiation are changing slightly independently would explain something. I don't know. Physicists is welcome to.
So changing the efficiency.
Yeah.
Yeah, but maybe that's an idea to explain it. I don't know. I just can't really imagine it. I think it's one of the things to look at here.
We will. Colin, I think you're next. Or no, excuse me, Sibylla.
Sibylla.
Yeah, hello. I found it interesting that when in the scoop experiment, when the ends were reduced to 0, that the output in all parameters was going down. It can be compared to shortening the bass bar.
Yes.
Did I get that right? Yeah.
Well, we evidently need some stiffness at the outer edges of the bar, except they went up on average a little in the bridge shell area there, or for part of it. But yes, it's fascinating. I don't have an answer. Maybe someone else could posit one. Well, actually, it made me think. It's kind of emulates a bit more the Baroque bars, where the bars were shorter, and so to the extent that the results carry over, I mean, there seems to be an evolutionary reason why we did lengthen the bar as well as raise its height. Colin?
I agree with Luca that, I mean, the changes are really quite small. And if the changes are really quite small, you'd expect a really linear variation with mass or with whatever parameter that one's actually using. So as you go from an extreme, from a physical point of view, what you would expect to see is a linear variation with mass or for small changes or arching or whatever parameter you use. And the interesting thing is that there is a paper in the literature that I wrote on the effect of bass bar height, bass bar mass, in fact, sorry, and showing exactly the sort of smooth variation as the frequencies change with the mass of the bridge and the amplitudes. And the interesting thing is that certainly in the high frequencies, up near the Bridge Hill area, where the rocking frequency and the dynamics of the island area are very important. There are predicted, in fact, from FEA measurements and from experimental measurements that you do expect to see some effect, quite significant effects, and perhaps I can talk about that next time.
Please do, yes.
Not now.
Mm-hmm. George?
So back to what Luca was saying, I think he was talking about you can't possibly have sort of jumps in frequency of things going up when you remove wood and so on, but you can with amplitude. So that's amplitude really here is of a lot more interest than frequency, seeing itself in general in the range we're interested in. The frequencies are hardly shifting at all. So really it's amplitude we should be focusing on, not frequency. And in general, it's a general trend that as you remove wood, amplitudes do go up, but actually not forever. There comes a point where you start to lose again. So there again, each plate can have its optimum. But the other thing is, I think we shouldn't really be sort of fixated on the bass bar as a single component. It's a bass bar in a context. So it's a bass bar in the context of a top of a particular type of material properties of an arching and graduation scheme, but it's also related to the thickness of the back, because a very useful and interesting measurement to make, although it's difficult to do it accurately, is a rotational admittance, where we look at how stiff the plate is in terms of the rocking of the bridge as a whole. So if you that rocking stiffness is also affected by the stiffness of the back, because it's connected with a sound post. So we should really look at that whole system a little bit more holistically. And so in the case of the Baroque violin, where you had bass bars that were considerably shorter than modern ones, maybe only like 5 millimeters high, but there again, they had bridges that were only 25 millimeters high, sort of, and a different string tension profile. So you want that rotational admittance is really the thing that's going to be controlling your a lot of your playability and your wolf notes. And so that's one thing. But this really only really applies to the low frequency end of the system. So at high frequencies, the bass bar is more reactive. It's locking the foot on the G side, and there tends to be more mobility on the E side at higher frequencies. So it's the whole system is quite complicated, and the different things apply in different frequency ranges.
I guess everything is illuminated.
Illuminated or eliminated. Well, I mean, I just think, well, in terms of doing an experiment like this, you have to start somewhere.
Mm-hmm.
So even though we understand that the whole thing is complicated, and then the judgment of it as what is actually an improvement, whether it's an improvement on this particular instrument or whether it's going to be a universal improvement on all, these things are extremely hard to assess. But you actually have to begin somewhere in the process, and we've done that. We have certain things that are sort of clearish, but not perhaps as telling us everything that we want. So what it really means is that if we wanted to do another bass bar experiment, we're better equipped to design it next time round.
I agree, and I would have loved to have these these results 20 years ago. I mean, it's good to have a starting point, and then you can adapt them to your model and to your experience. And these answers are by definition general, and we wouldn't expect them to work for everything. But for the same reason, people all use bridges roughly the same, width and height, and many other things. We just take a measurement because it works best in general. So I think we actually have one that perhaps will work out that way. And I'm very relieved that it's not far from common practice. I mean, as MJ said, keep doing what you're doing. And if it was far, then I would be a lot more suspicious of our measurements. The fact that it came close to me kind of reaffirms the validity of the test. John Hart.
Yeah. Hi. Thanks, Joe. Joe, what was your skew scheme used in this experiment?
Skew scheme? What does that mean?
How much was the bass bar skewed relative to the center line? Center joint.
Alex, remind me. Alex, by the way, was sort of the overseeing the making side, and my memory is not good. What did we decide? They would go in at whatever people normally did, or?
Yeah, I think in general we just had people do what they would normally put in their instruments. Both for the angle and also for the length of the bass bar. At some point, we considered having a uniform length of bass bar just to have everything more controlled, but also we weren't controlling for the length of the plate, so that didn't really make a whole lot of sense. So we just had people do whatever they normally do.
It's kind of like the question of, should you put the same strings in all instruments for a playing test, or is it the case that makers will pick the best strings for that instrument? And there's a bit of a sense there that makers do what they do. I'm sorry, John, did you have anything else to add?
Not really, other than Norman Pickering way back noted the effect of skew on, I think, the A0 mode. So, if you do skew a bar more, well, okay, you've got a slightly stiffer plate, but I suppose you can compensate with that, by using a stiffer bass bar if you don't skew the bass bar as much.
And just to be clear, by skew you mean angle from the vertical, or from the perpendicular, or do you mean length along the length of the plate?
Yeah, along the length of the plate. Yeah, relative to the center line.
I see.
See. The standard thing that I use is the Saucony 1/7 division system, but I don't know what others use. But that's I guess what I begin shooting for. But and I've always done that, but so that I've got some sort of consistency. But I do know that people. I think Sam Zygmuntowicz did an experiment with a bass bar adjustments at one point, and he was replacing bass bars and skewing them a little bit more or a little bit less, and seemed to generate some sort of effect from doing that.
Mm-hmm. Well, one reason that to skew it at all is that it's going to help stop cracks from developing along the side. So we want to do some. I suspect that's how it originated. And then the other notion is have it in proportional to the width of the bouts, in which case we would expect it to change a little as that changed. And but that's a good point. One more variable we could have nailed down a little better.
Oh, well, thank you very much for this. This is very interesting.
Thank you.
Yeah, Joseph, at this point, since doesn't seem to be any more hands raised, I think it might be interesting to, ask some people what are their shop practices and beliefs about bass bars. And since John mentioned Sam, I'm wondering, if Sam has anything to speak about the subject, and also in particular about the skew business. I do remember many years ago at Oberlin, Sam brought an instrument, and when Renee looked at it, I think he suggested possibly skewing the bass bar in that particular instrument. I don't know if my memory is correct, so maybe Sam could talk a little bit about that.
Is he with us?
Let's see.
He was.
Hello. Am I here?
Yep, go ahead, Sam.
All right, I'm busted. Well, it is just about the topic of skew. There was a period where I thought, well, when you turn the bar, of course, you are avoiding cracks, as Joseph says. And I thought, well, you're also crossing more cross-grain lines and a little stiff in the plate, and that seems without adding any weight, and that seemed like a good bargain to me. So there was a period when I had instruments that were a little bit, I thought, floppy or whatever. I would turn the bars like an additional millimeter or something. I've stopped doing that quite a while ago. A number of those instruments, I took out the bar and put in a straighter bar, and I found that they were the sound was a little bit, it's not a technical term, but a little nasty with the turned bar. And I think my understanding of the bar is quite different than it used to be. And that it's not just to be stiff, but it's meant to be actually, if you want to think of it that way, the top has to be flexible in the island area to allow the bar to move and pull down and activate the ends of the instrument, if you know what I mean. So turning the bar locked it up in the island so that it couldn't as effectively activate the ends. And so some of those instruments, I found that, for example, making a bar straighter but larger was more effective than turning it. Well, if you want, I have some not very ready for prime time stuff that I could show you about.
Okay, wait a minute. Let me. I need to make you a co-host. So a second, I have to find you in the list of people and make you co-host.
Let's see if I can find it.
Okay, go ahead.
All right, I just have to see if I can find this thing. Okay, well, here's one little interesting thing. Let's see. I guess I have to share a screen, but. What the hell? I was looking for, like, there are other aspects of it. So I'm going to share screen for a second. How do I do that? Okay. I'll apologize to Sebastian here. I mean, we've been involved in a long project to try to take my information and regularize it and try to find more statistically sound correlations. We're about just partway through that process. So as of right now, a lot of the stuff I'm doing is you could say without adult supervision. So right here, one thing that interested me when you put a bar in, this is not related to the skew anymore, but one thing I noticed is when I was looking at the difference in M5 from when you put from the plate without a bar, then after a bar, how much does the M5 go up? And I was trying to find a metric for how stiff you should make your bar. And I thought, well, maybe the amount that it goes up in M5 is a pretty good signifier, that maybe it should go up the same amount and you wouldn't care about what the actual pitch was. And that was a little theory for a few minutes. But I think what I've since found is the opposite. That's, some bars I would say it goes up an average of like 55 Hertz or something like that with and without bar. But some might be as little as 45 and some might be a little more, up 60, 65 even. So what was that telling me, if anything, about the plates? So let's see. Okay, well, I'm not going to go all through it, but what you have, can you see my screen?
Yep.
Okay, so I present this with potential apologies. This is the best I can do for right now, and I don't swear by it. So this right here is the amount of rays of M5 with or without the bar, and like on my set, it goes from 42 Hertz up to, well, there's one that says 80, but I don't know if I believe it, but 70 anyway. Over here is the Bridge Hill spectra, and this is all on Guarneri models, and it looks like there's about I don't know, 25 instruments roughly. So I wouldn't say that that's a super robust trend, but I would say that the instruments where it went up less seems to me to be slightly a slight trend to being a little more output in the Bridge Hill. And this little trend line, if you want to believe it, shows, I think, a soft trend downward as the amount of Hertz increase. And I thought, well, what else does that, and that's sort of interesting.
Sam, could I interrupt and ask, this is for the same height bar put into each, or?
My bars are pretty consistent, really. It's not controlled for the heights of the bar. So it does not take into account any variation in my bars.
And do you vary your bars according to the shift in frequency, though?
Not really, no. I did that for a little while, and I think it's actually probably a mistake. That I thought if they didn't go up as much, maybe I should just leave it higher, which would then force it higher. But I think actually, in retrospect, that's a logical fallacy. That's the opposite. That it's not going up as much because the plate is already stiffer, so the bar, relatively speaking, doesn't have as much effect on it. So I don't have a real answer, but that's just what I'm finding here. And just a few other things on this theme, and then I'll drop it. This was the amount of rise with M5 without the bar. And I would say, once again, a rather weak but existing correlation. This is a correlation of the amount of rise to top without the bar Harris number, which is like the Evan number, basically. And here's the same thing with just the mode 5. So, I mean, that's just a small detail. I don't want to dwell on it too much, and I'm not reading too much into it. But it's just to say that there's a lot of other factors with bars. So that's all I have to say about that one there. If you give me, do you want more of this? I mean, I have a lot of other not ready for prime time stuff that I could talk about, but.
To start off, you say you do about the same bar all the time. Could you describe that bar so we know what you're talking about?
Yes, I put a normal bar in.
And that would be
no, I measure through the plate. Usually about 14 to 14.5 or 14.7 through the middle, and somewhere between 11 and 12 at the quarters. I tend to leave the last eighths a bit on the high side. Another subject which has been talked about a lot is tension. So I've been doing a lot of tension experiments lately. It's a little bit of a obsession of mine now. Is the contours of the arching, the relative straightness through the island in particular. So I have a series of instruments which, I had put in bars during a period when I was using sort of a René bar, which was 1.5 millimeters of tension at each end, which makes the arch a fair amount rounder. And so some of those instruments, if I was unhappy with them, I was taking out the bars and putting in bars that were zero tension, or sometimes extremely zero. I can show this stuff quickly. I'm just going to say that take it for what it is. I mean, if I read this, I don't consider this, scientific level documentation. Let's see, is this working? No. How do I make that work? Okay. Well, this is just, I'm going to zip through these, but in this case, blue is before, red is after, and one had a quite heavy tension bar in and later had no tension. And what I thought was interesting about it was it didn't actually help with the, well, actually, in this case, it looked almost too good. A little more on the bass, a lot less in the transition hill, and arguably a little more in the bridge hill. And this is just from well, to be honest, usually when I take a top off, I can't resist taking a little nibble off the thicknesses somewhere, so it's not a very pure test. This is another one, more recent, same thing, bar with no tension. And one of the things I thought was interesting is, this is not super changed. Really, the change that I saw a little bit more was more output here in the bridge hill, which I think, well, I have my personal explanation for it, but I just thought it was an interesting thing to observe. Here's another fiddle. read after. In this case, it was a little less in the transition hill, which I thought was all for the good. And I thought a little more in this same region, the upper part of the bridge hill. Oh, that's on the back, never mind. This is another fiddle, same type of intervention, and a similar sort of, a little bit of a haircut in the transition hill, and I believe a little more output in the, well, in this case, a little lower part of the bridge hill. This was a bar before and after that was turned. And I think it's kind of similar. I think that if in anything, when you have the island area too stiff, either from turning the bar or from having too much tension, that you're not letting as much energy get out to the ends. This is another new bar, and you know, it's not major changes, but if I look for it, I think you know, with the new bar that was a little stronger, I think I see a little bump here. Yeah, anyway, we don't have to go through all this. So just to say that, I don't want to go on and on. That's just some stuff I've been doing.
Thank you.
Next.
Colin, you're muted. Colin, you're muted.
I apologize that I have to go. I'm supposedly on holiday with my wife. You'll understand, I hope. And it's been very interesting indeed, and I look forward to the next session. Thanks,
Thank
everyone.
you, Colin. Bye-bye.
All right.
Yeah.
Thank you, Colin. Bye.
Someone had a chat question. Does anyone see that?
Which one? Let's see.
Oh, David Van Zandt, are bars generally fit with a ring or without? I'm not sure. David, what does a ring mean? Is David here?
Yeah, he's still logged in.
Is he muted?
Stabilizing ring.
Bass bar frame, maybe.
Oh, bass bar frame. Oh, I certainly always do. Alex, was there anyone at the experiment who didn't use a frame?
Yeah, I didn't ask, actually.
Don't ask, don't tell. Okay.
Yeah, yeah.
George?
Just since we've got a bit more chatty, I'm just following on from Sam. I mean, one of the main effects of the bass bar is to actually increase stiffness of the plate. And I find I've started sort of logging in my individual instrument spreadsheets the bass bar rise in frequency as a percentage, not as an absolute number. Because I mean, if you started off with a mode 5, say at 280, you know, sort of 50 hertz is a bigger proportion than if it started at 320. So having it as a percentage tells you something. I find there's really quite a wide range from one instrument to another. You know, I have seen, you know, as much as 60, but sometimes 60 hertz rise. Can't remember what the percentage is, but yeah, but sometimes it's quite small. And you know, for various other reasons, I wouldn't particularly want to do anything very different there. There was something else I was going to say. What was it? Oh yeah, when another sort of bit of low-hanging fruit you can get is if you do the Evans numbers or recording 2 and 5 is looking at the 2 to 5 ratio, and that can be quite interesting. Sometimes that definitely shows a peak as you go start going down from thick to, you know, reducing the bass bar. There's a point at which it reaches a maximum. Now that's not always the case, but sometimes it is. And how do you interpret that? I mean, I think for one way to interpret that is that you're making, if that ratio is high, you're gaining more benefit from the arching. So mode 5 is much more dependent on the arch than mode 2 is. And therefore, as that ratio increases, you're getting more more of a lift to mode 5 than you are for mode 2. So in general, that's not quite a good thing, and can be a helpful thing in that decision of whether the bar has been reduced enough. So
George, what is your sense of a normal bar? What would you, in your practice, what would you normally?
I tend to be around about 12 millimeters in the middle. I tend to put the highest spot a little bit above the bridge position, but keep a fairly consistent height for between the bridge towards the upper F-hole eye. But then I have quite a lot of scoop after that, particularly in the lower bout. Now I make my ends actually rather quite smaller. I've not, but there again, I've not really done any systematic experiment to see what I like there. But I have found that I do prefer a little bit more scoop. But I've tended recently to move. I've been a bit more careful about picking reasonably low density wood for the bass bar. Something like about 0.36 seems to be nice for the job. And it's not very easy to find something a lot lower. Easy to find something high, of course. But I tend to make them more sort of parabolic in cross section, so more towards a knife edge at the top. So there's a bit more stiffness there at the expense of mass. I mean, if we look at the other way around, how much what's the mass costing you in frequency? So if you make that kind of profile, you can come down a bit in mass. And
do you pay attention to how much it raises the tap tones? I mean, is that one of your controls, so to speak?
Yes, but I mean, I wouldn't, because the whole thing is a little bit elusive. I wouldn't want to rely on any one single number. It's part of a collection of things that I can look at.
Mm-hmm.
So I'm looking at the percentage rise of mode 5, right, as one parameter. The ratio of 2 to 5, the Z value, the mass of the bar, a sort of collection of things. And if the sort of confluence looks good, like as the Greeks said, birds to the right is a good omen. So if all these things are approaching sort of happy zones, then I think I can't be very far away from what is a good choice for that bass bar.
Mm-hmm.
But I could be wrong. I mean, I have just been wrong, actually. An instrument I finished early this year, I think I left it a little bit on the large side, and I may have to have the instrument back and take it down a little bit.
I found that one of the striking things about this experiment is that the instrument that I put in was made from a throw-out top of mine, meaning I thought it was a bit heavier than I was going to use, and a few other factors, and it was put onto some spare ribs and another back. And with the bar at 14, when we strung it up, I thought it just sounded terrific, and it measured really well. And I have, over the last years, been reducing my bar somewhat to get a bit more bass. My instruments were getting where I felt I could get a more balanced sound that way. But in light of that, I'm I think shooting back a little bit. But I've had actually some very good instruments, I thought, with bars as low as 10.5. I don't really go much lower than that.
But that might be because you're probably working with a very low density wood.
Well,
therefore the kind of proportion of added stiffness needs to be a bit less.
Yeah. Well, I mean, I use the same lower density bass bar wood, but again, we're talking, I have used some very low density wood, but in past years, about 0.34, I guess, 0.3 to 0.36.
That's at the low end of the range for sure.
Yeah. But I would have thought if the bass bar was the same density as the top, and one varied them together, then that should take care of itself. But at any rate, the height is going to make so much more difference to the stiffness than the density or the strength of the wood, just because of the cubed effect. But I don't have any answers, any hard answers, except I do think that this has been illuminating for me in terms of, oh, try a little more scoop, see what happens, and you know, take a current norm. I'll go back to maybe 12 instead of starting at 11.5 or something like that. Mm-hmm. Any other makers with thoughts about what they do? Robin, we'd like to hear about cello bass bars.
Yeah, but Georgiou has had his hand up for a while. Let's
excuse me.
First, and then we'll go to Robin, okay?
Mm-hmm.
Yeah, just a general question. If anybody else has experienced this, sometimes I'll put a bar in and mode 5 is just mode 4 or 5 or 5 and 6 are very relatively close to each other, and I really can't tell what is what. And the higher mode is maybe way too high for what I'd like in mode 5, and the lower mode is way too low to be mode 5, and I'm kind of stuck in trying to decide whether or not I want to take the bar down or not. Does anybody else have this situation where two modes are very similar or close to each other, and you really don't know what to do with it? And the bar isn't necessarily high; it's maybe about 13.
I think I partially answer that one. This is actually an ongoing problem. Like it's not an uncommon thing to say have mode 6 so close to mode 5 that that's the one you keep finding when you're looking at the tap tones. So the only real solution there is modal analysis, in which case, even if they're at exactly the same frequency, you can still separate them.
Okay.
I find it more common that your mode 5 is close to mode 6 than that mode 4 is close to mode 5.
I didn't know which was which, but just two modes in that area are really close to each other.
Yeah.
Well, can't one just hold it at different positions? I mean, where are the antinodes and nodes for mode 6? Is there a point where you can eliminate mode 6? And
well, you can do that part. You can help yourself definitely by where you excite it and where you hold your. If you have a movable microphone, you can choose an excitation point and a measurement point, and you can also hold it, say, where one mode has an antinode and the other one has a node. Then you can quite often split the two up.
Where would that be for mode 6, as that seems to be?
Well, mode 6 is a more of a left-right symmetric mode. So along the center line at the block ends might be a point where you could do that.
Yeah.
You need to hold it at the block lines.
I mean, if you want, if you give me a few minutes, I could get up on the screen a couple of the modes, mode 6 shape, so you can see. Would anyone like me to do that?
Yes,
please.
Yes, take me a few minutes to do it, but I'll do it, no problem.
Luca, do you want to say something in the meantime, or do you want to wait?
Yeah.
Okay.
I just was going to mention, you can also, if modal analysis is a little bit too involved for you, can just build a Chladni table and see the mode shapes that way. And for me, it's usually pretty easy to separate 6th and 5th mode just through that, and it's much cheaper and easier.
Good point. And Doug?
No one's mentioned mass yet, it seems, on the bass bar. I've always been imagining the scooping of the bar sort of isolates some of the central blob of central mass that has a reactive reaction in the dynamics.
Yeah, we've made passing references to the mass and not controlling it. Well, anyone have any thoughts about that? I don't know. I have my set of habits, but if I add mass, it changes things a little bit, but not very much. Well, I'm curious to know what people think of as a normal bass bar mass. Mine typically are 3.5 to 4 grams, which I think is on the light side. I think an average from an old thing I did for old Italians was, around 4 to 4.3, something like that. But anyone have any thoughts on that?
Yeah, well, my thought is experimenting with little blobs of clay or lead right near the bridge foot.
And did you find something from doing that?
I haven't done that.
Ah, well, I think I've stuck clay just about everywhere you could stick it on an instrument, and I found it very good. Like in some points with the bridge, of course, and on the treble F hole wings and the edges of the F holes, all those make a difference. But along the bass bar, I just haven't found it that sensitive.
Okay, yeah, I take that.
Okay.
George?
George?
I think George is back.
Yeah, just a second.
You need to make him a co-host.
Oh,
Yeah.
Thank you. There you go.
Okay. Right, so share screen. I was hoping to so that's a kind of typical mode 6. So the mode 5 nodal lines tend to sort of come around like that, or sometimes they come through the F-hole eyes. So if you were holding it with your fingers at the middle of the top block and hit a little bit to the right or the left, or in the widest point of the upper bout, you would be exciting that mode, particularly if you tapped it hit round here where the mode 5 nodal line is crossing. Then you're more likely to excite mode 6 than mode 5, or it'll be a larger amplitude. And likewise, if I can perhaps try again. There's mode. Oh, that's what I wanted. I wanted the two up together. So if you could hold the plate, say on the center. Can you see my mouse?
Mm-hmm.
On the center line near one of these nodal lines, you would not so much the bottom one because it's close to a nodal line there, but at the top area, if you could hold it there in the middle, you might need quite big hands. Then you would tend to get mode 5 more than mode 6, or likewise at near one of these corners, or so fiddling around. I think you can selectively increase the amplitude of one and suppress the amplitude of the other, so you can separate them out. But you can do it with a combination of things of holding it to damp out that mode. Although mode 5 is a harder one to damp out because there's a lot of in-plane motion. But you can also choose where you put where you tap and where you put the response. So obviously along a microphone very close to the surface along that nodal line will tend to suppress mode 6, but it will enhance mode 5. Is that okay?
Very good.
Let's see if I can go back. Oh, here it is. Can't seem to stop the share. That's what I need to do.
Oversharing is a problem.
Does that help?
Yes.
Yeah, it helps.
I wasn't really paying attention to what Luca said. I think Luca was saying something about doing this something similar. Is that right?
Yeah, I just said you can use a Clutton table to get similar results in a more simple fashion, basically.
So doing what?
Building a Clutton table. So exciting the plate and having some kind of sand or tea leaves on it and just seeing that they collect at the nodal lines and then just visualizing the nodal lines by that, and then identifying the mode from the nodal lines.
Yeah, but this is difficult if they're very close in frequency. Then your mode 6 tends to be rather higher amplitude than mode 5, so it tends to swamp it, and it's hard to identify where it is.
Yeah, I think it can very much depend on your
can be helpful.
Yeah.
Yeah.
Could I just add a comment in on what George just said, because no one has said it? Anything you do that makes two modes come close together in frequency, the shapes are also likely to mix at the same time, and that may be part of the confusion. This coupling thing that I've talked about in a previous talk, this will be a good example of that. So if you could do something with the bar that actually made two of the free plate modes really close together in frequency, then I wouldn't necessarily expect the shapes to look like their usual things. Modes 5 and 6, you're going to get mixtures of the two usual shapes when you're right near that that coupling point. That's a universal behavior.
Now, is George Yu's hand still up? Maybe not. Robin? Cellos?
Am I audible?
Yes.
Yeah, great. Yeah, I've been sort of scratching my head trying to think what I can say that's got some universal truth or relevance. And I had one experience where I scoop, from the sort of the quarter points of a bar, and there was quite a lot of mass in the middle, and I ended up with unable to control the bass response of the instrument through adjustment. And so that was, for me, that was a big lesson, to just thinking about the amount of mass in the middle of the bar and how scooped away I am in the quarters, just to not let that get out of control. And also that these quarters are going to, if you want to support your treble response, don't lose too much wood from there. I had this experiences that make me think that bar height in the area between the top of the F hole and around the upper corners, that seems to be also connected to treble response for some reason. And so, these bass bars that are very sort of asymmetric, towards the bottom of the instrument, I would assume would be darker bars, whereas a bass bar design that is more symmetrical, I would think would tend to be a brighter bar from that viewpoint. And but this, for some reason, this area, above the center point of the bar, in this upper corner area, does seem to be strangely connected. And I actually found for one of my models, getting rid of material from there was good for the model. Those are the things I feel most confident about saying. I do try to find a bar design for each of my models, given that I try to make them really different. And people said, well, your bar should reflect your arching. Well, how should it reflect your arching? And so this has been a sort of through trial and error, trying to sort of customize the design of the bar to the model of the instrument. And I have there was one other thing. I guess, what I think mostly new instruments need tighter posts than old instruments. And I think maybe newer instruments need slightly stronger bars than old instruments, because they're not, for the same reasons. We're dealing with rather elastic young instruments that haven't been through their sort of settling down and distortion process. And So I think that's that's just something I bear in mind. I don't mind being going to sort of slightly higher bar heights that might be considered very very conventional. And if I were doing that, of course, I'd be also looking at using lower density wood in order to not end up with, you want to support the treble response of an instrument. You want it to be brighter. You need stiffness in the bar, and you don't want mass. So you make a bar that's higher and lighter. So that's helped with some instruments, where I've been working on a kind of a prototype model that I've not sort of got sorted out, or I'm struggling to make a model work the way I want it to.
And do you find, I know you do, or you've told us in past sessions about sticking little bits of stiffener on the outside. Do you do that over the bar, for example, in the upper section? And that's a good determinant of whether it's going to work or not? Yeah,
absolutely. Yeah, you can stick stuff, I when I'm doing this, I mark my bar, but with a grease pencil or something on the outside of the instrument. So I can see exactly where it is. And you can make yourself a little strap that is positioned and lying exactly along the bar. And, you want to feather it. You want to make something that's a modification you would be prepared to make to your bar. So they're usually tapered off, and you can test, stick it on the outside and see if that's good for the model, good for the, would that be a better idea for the bar? And you can have little enhancements at the ends to see, should I have left my bar thicker at the ends? Things like that.
And remind us how you stick them on.
Okay, this is so these all of my straps are made of bassbar offcut, so they're wooden straps, and I fit them very accurately, and I glue good paper to them, and I glue the paper on with a margin of about 1 millimeter, and I glue them on with hide glue. And the paper margin around the edge of the straps are really important, because if you don't have it there, you can get the glue bridging round the paper to the varnish. But if you take the strap off within a few minutes, there's sufficient moisture in the paper that it'll actually just peel in half. So you'll end up with half the paper on the instrument and half the paper on the strap.
So it's hide glue sticks the paper to the bass bar stock, and then what sticks it to the varnish?
Okay, sorry, I've pre-papered my straps. I might even have some. I could go and fish them out. So the straps are all made and fitted and papered and dried. And that's with hide glue. And then just before I stick them on, fairly thick hide glue actually, because you want it to grab in a short time. So you've brushed it on, you've pressed it onto the plate, you're twisting and pushing a little bit just to see if it's bonded to the varnish, and once it's stuck, then it works. You can play the instrument. So maybe you're only talking about a very short time between trying the instrument with the strap, without the strap, and trying it with. And then if you remove it within a few minutes, you don't need to wet the paper or do anything. You can just actually take it off, because the paper's got sufficient moisture to peel in half. If it's there for longer, you've got to undermine the paper to get the strap off. And for straps I'm going to leave on, I perforate them so that I can get the water through the strap to the paper, so that all the paper can be wetted, and not damage the varnish.
And so you leave some straps on the outside of the instrument if it works there?
Yeah.
It's on underneath the fingerboard effectively?
Well, I don't leave that. They don't go out into the world like that usually. No, I take the front off and put them on the inside.
Okay, well, that's fascinating. I didn't realize that hide glue would actually hold wood to varnish.
Yeah, very well. and that's why you need the paper in between. And yeah, it works beautifully, actually. Yeah.
Well, that's just great. Sam created a lot of excitement years back with the Gluey project, and we've often meant to get back to that. But for adjusting bass bars in the way you say, marking them out, that seems an ideal way to. We could try a bunch of things at a workshop quickly. So thank you for sharing that. That's
a huge pleasure. And you know, and I have to say this: what I'm doing is completely inspired by the Gluey project.
Okay.
I read the write-up of that project and thought, this is just the most powerful experimental tool I could possibly imagine. And I can never resist it ever since.
Well, thank you, Sam, for that.
Yeah, thank you, Sam. Yeah.
All right, are we about to wind up?
It looks like it. And just to announce again that we're going to have Bass Bar Part 2 in December. So we're going to move Jim's Wood Talk to January. Okay, you'll get an announcement and you'll have to re-register if you already registered for the December talk. So thank you very much for all of our panelists and participants, Joseph and MJ and Sam, and for Robin for commenting on this and all of your questions. So this ends our formal portion of the session, and as usual,